Molecules with carbon-carbon double bonds are called alkenes, and molecules with carbon-carbon triple bonds are called alkynes. We are going to start off this section talking about molecules with triple bonds, the alkynes. Then we will talk about molecules with double bonds, the alkenes. Finally, in the last part of this section, we're going to talk about molecules that have both double and triple bonds in them, and you'll learn how to name those. To name a molecule with a triple bond, you're going to follow these steps. First, you're going to find the parent structure. So you're probably sick of me saying this, but it's the longest chain of carbon atoms in the molecule. But in this case, when we're naming alkynes, the longest chain must contain the triple bond. And so we're going to name it for the number of carbons in that long chain plus the ending -ine, Y-N-E. So in this molecule below, there are 4 carbon atoms. 1, 2, 3, 4. So there's 1 carbon on each side of the triple bond here, and the lines extending out from the triple bond are to another carbon atom. Remember, when it just ends in a point like that, you've got a CH3 group and a CH3 here. So in case you forget, this is what the skeletal notation of an alkyne looks like. So there's 4 carbon atoms. So that's going to be butene. Then we would find and name any substituents if they were on the molecule. This one has none. And then finally, we're going to assign a locant to the triple bond. So we need to number the parent chain so that the triple bond gets the lowest number. And this is different than anything we've done already. We're prioritizing the triple bond here for the numbering. So it's more important than those substituent functional groups that we've already learned, and it's more important than any alkyl groups you might see on the molecule. Any other substituent that you see is numbered relative to the number that you give the triple bond. So in this case, we would just number our carbons 1, 2, 3, 4, and we could number the other direction 1, 2, 3, 4, but in either case, the lowest locant that we could give the beginning of that double bond is 2. And then we're going to put the name together. So we do the longest chain, bute, we put a dash and we add the locant, 2, and then another dash, and then the ending -ine, bute-2-ine. Let's do a few practice problems naming alkynes. So here we have a nice molecule. Let's first find the parent structure, see how many carbons there are. So 1, 2, 3, 4, 5, 6, 7, 8. So our parent structure is going to be named oct for 8 and -ine for an alkyne. Highlight that in pink so you can remember it's the parent structure. And then we're going to look for substituents. So we have a chloro substituent here. Chloro. So this will be a chlorooctine. Now we're going to find the locants. So we have to prioritize the triple bond in our numbering. So we can see already that the triple bond is closer to this end of the long chain. So we're just going to number from this end because we know that that's going to give the lower numbering to the triple bond. And we can tell that if we start at the other side, it would just be a much higher number. I just threw my pen. We can tell that if we start from the other side, it would be a higher number. So 1, 2, 3, 4, 5, 6, 7, 8. So our triple bond starts on carbon 2, and our chloro substituent is on carbon 6. So we put those locants in, 6 chloro oct 2 ine. The next problem is asking us to draw a molecule. I haven't done one of these yet, but you're going to see it a lot more throughout the course as we move on. So draw 4-butyl 5-ethyl oct 2-ine. We're going to start with the parent structure, okay? So I'm just going to highlight this in pink. First, let's just draw our triple bond to start off. That'll make it easier. So opt2-ine means that the triple bond's on the second carbon. So we just need to draw one carbon on the other side of the triple bond. That'll make this 1 and this 2. Then this one is 3. And then we need a total of 8. So we'll just draw 4, 4, 5, 6, 7, 8. I'll just highlight those for you. 8 carbons. Now our substituents are a butyl group on carbon 4 and an ethyl group on carbon 5. This would be carbon 4 here, and this is carbon 5. I'm just going to move this 4 below so I can draw the butyl group. Now but is 4 carbons. So 1, 2, 3, 4. And ethyl, as we know, is 2 carbons. I'm going to move the 5 again. I should have drawn them on the opposite sides. So 2 carbons on the number 5 carbon. 1, 2. So there's our molecule, 4 butyl, 5 ethyl, opt2-ine. You might run into situations where you've got multiple triple bonds in the same molecule. These are called polyines. And what we're going to do is we're going to do our very best to include all of the triple bonds in the molecule into the parent structure. To name the parent structure, we're going to take the number of carbons, we're going to add the letter A, then the multiplier, so di, tri, tetra, whichever one corresponds to how many triple bonds you have, and then finally the ending -ine. So this seems a little complicated, but it'll make more sense when I go through this example. Here's a molecule with a couple of triple bonds in it, and let's count the carbons. 1, 2, 3, 4. So there's 4 carbons in this molecule, and there are 2 triple bonds. The word for 4 carbons is but, and then we're going to add the letter A, buta, and then a multiplier, so di for 2 triple bonds, and then ine. Butadiene, butadiene. Now we put the A in there because it helps the molecule sound nicer when we pronounce it. If we didn't put the A in, it would just be butadiene. That sounds a little rough. So the friendly folks at IUPAC decided that they would stick an A in there for pronunciation's sake. So butadiene. And to be more correct, we would actually prefer to add the locants in here. So 1, 2, 3, 4. So the triple bonds start on 1 and 3. So this is buta 1, 3 diene. Now it's rare that you will encounter this, but you may encounter a situation where you can't actually include every single triple bond in the parent structure chain. So in this case, you're going to name it as an alkynyl substituent. When we're naming an alkynyl substituent, it's just the number of carbons in the substituent plus -yl. So YNYL. So it's a combination of -ine for the triple bond name and -il for the substituent name. In this molecule is the example that we have here. So this is 5-ethynyl nona-1,8-diene. So I'm just going to highlight the substituent 5-ethynyl, and I'm going to show you where it is on this molecule, also in orange. So that's a 2-carbon substituent, F, and then -yl because it's the substituent. And the 5 comes from where it is on that main chain. It's on carbon 5. So now that you're a pro at naming molecules with triple bonds, we're going to move on to naming molecules with double bonds, the alkenes. So to name an alkene, you're going to follow these steps. We are going to find the parent structure first. So in this case, it is the longest chain that contains the double bond. We're going to name it for the number of carbons in the chain plus the ending -ene. So this example below has 1, 2, 3, 4 carbons. So that is a butene. If there were any substituents on the rest of the long chain, you would name and alphabetize them, but there aren't any on this example. And then we've got to assign a locant to the double bond. So we're going to number the parent chain so that the double bond gets the lower number. This is similar to the example with the triple bonds. We're going to prioritize the double bond over any other substituent that's on the molecule, and any other substituent will be numbered relative to the double bond. So in this case, if we number our chain, we've got 1, 2, 3, 4, and so the double bond from either end would start on 2. And so putting the name together, that would give us bute 2 ene. And so I'm following the convention where we take the longest chain, we put a dash, the locant, a dash, and then the ending ene. But wait, we have a problem. If we look at these two molecules on the bottom of this page, it turns out that we would name them both bute-2-ene. So on the previous page, we just named this molecule here bute-2-ene, but this molecule on this side also has 4 carbons and it has a double bond that starts on carbon 2. So we would also call this molecule bute-2-ene. These two molecules are configurational stereoisomers. So that means they have the same formula, the same connectivity, but the three-dimensional arrangement of their atoms in space is different. Double bonds are not free to rotate. So let me show you that. I have a carbon with a molecule with a double bond here. And remember, they're rigid. They don't rotate, so we can't interconvert these two stereoisomers. They are truly, truly different molecules, and they have different properties. And because of that, they really do need to be distinguished. They have to have different names. So there are a couple of methods that the nomenclature folks have come up with to give us a way to give these two stereoisomers different names. The first convention that we can use to distinguish between the stereoisomers is the cis and trans nomenclature. So that's generally used when there are two identical groups on either carbon of the double bond. So for example, there has to be a set of two identical groups on this carbon and on this carbon. So generally you'll see this when there's a hydrogen on each side, on each carbon. And what we're going to do is we're going to consider a plane going through the double bond containing both of the carbon atoms. So if I was to hold my double bonded carbon like this, I would imagine the plane would be going right through here, cutting this way through the molecule. Now, if the two identical groups are on the same side of that plane, so if they're both on this side or if they're both on the back side here, we're going to call that geometry cis. And if there's one on either side, so here's my plane cutting through, and if there's one on this side of the plane and one on that side of the plane, we're going to call that trans. So we're going to look at our example here. So on the left, we have the butene. Remember, here's our 4 carbons for the butene, and on those double bond carbons, there are hydrogen substituents. We didn't show them before in our skeletal notation, but we're just showing them here. And those hydrogens are on either side of that imaginary plane here. So it's trans bute-2-ene. And in this representation of the butene, we have those hydrogens and they are on the same side of that imaginary plane, so it is cis bute-2-ene. Now, the other way that we can distinguish between these two stereoisomers is using the E and Z nomenclature. This is more powerful and it's more useful in a more broad variety of applications. In this convention, we are going to look at each carbon separately, and then we're going to find which is the higher priority group on each carbon. Then we're going to consider that same plane going through the double bond containing both carbons. So cutting it like this, like there's a big wall going through. And if both high priority groups are on the same side of that plane, we're going to call the molecule Z. Now, Z comes from a German word called zusammen. It means together. And if the two priority groups are on opposite sides of that plane, so one on this side and one on the other side of it, that's going to be called E. And E is another German word for entgegen, and that means opposite. A way that you can remember these to keep in your brain is that Z is for Zaimzide with Zs, and E is for enemies. They don't want to be together. So in our examples below, I'm going to just tell you that the carbons on the CH3 groups are the high priority groups. I will tell you how to determine priority in the next slide, but for now, we'll just say that those CH3 groups are the high priority groups around the double bond. So in this example on the left, the high priority groups are on opposite sides of that imaginary plane. So we're going to call them E, E-but2-ene. And in this case, the E and the Z notation that is placed before the name of the molecule is in parentheses. And then here in the right side, we have the priority groups on the same side of that plane. And so that is called Z, Z-but2-ene. So now that you know about the E and Z notation, you're going to have to know how to decide which group on a carbon atom of a double bond has the higher priority. So we're going to use the Kohn-Ingold-Prelog rules. And for the two groups that are coming off of the double bond, you're going to compare the atomic number of the two atoms that are coming off of the double bond. So the higher atomic number has priority. So for example, I've got just like half alkenes drawn here. So for example, coming off of a carbon in this fake half alkene, we've got a carbon and a chlorine. So carbon versus chlorine. Chlorine has the higher atomic number, so chlorine has the priority in this case. If the two atoms that are coming directly off the carbon that you're looking at on the double bond have the same atomic number, then you have to consider the atomic numbers of the atoms one bond away, and the higher numbers take priority. So let's look at the bottom example. So here's our double bond carbon. Now the first atom that's off of the double bond is carbon in both cases. So a carbon here and a carbon here. And so we've got to look one bond away, and we're going to make a list. So bonded to this carbon on the top here, we have a CH3, and then it would have an H and an H. We don't generally show those, but they're there. And then this carbon has a chlorine, a CH3, and a hydrogen. The side with the chlorine atom wins because you've got CHH versus CHCl. And so you have a higher atomic number, one bond away here. And so that is going to be the priority group. So this whole side is the priority. So let's do a little bit of practice because I know that was a lot of information and it does make a little bit more sense when you're going through actual examples. Okay, so our first example, we're going to find the parent structure, the longest chain with the double bond included. So 1, 2, 3, 4, 5, 6, 7. So 7 carbons, that's a heptene. Okay, for substituents, we've got a fluoro and a 1 carbon substituent, so it's a methyl. And fluoro starts with F, methyl with M, so fluoromethyl. Heptene. And we've got to do our numbering and find our locants. So we're going to be prioritizing the double bond here to make sure the double bond gets the lowest numbering that it can. So if we go this way, we get 1, 2, 3, 4, 5, 6, 7. If we numbered the other way, so this way, 1, 2, 3, 4, our double bond would start on 4. So that's not as good. So we're not going to number that way. We're just going to stick with the first one that I did. And so that means our double bond starts on 3, our methyl also on carbon 3, and our fluoro is on carbon 4. So we'll put that all together. We've got 4 fluoro, 3, oops, forgot my dash. methyl hept 3-ene. Sorry you have to look at this frozen shot of my face while we finish this problem. Something went wrong with my recording. So we need to just add the stereochemistry to this molecule because we can see we've got this alkene and there are 4 different groups bonded around that double bond. And so there could be 2 isomers of this molecule and we need to specify which one we have. So remember, we're going to look at this plane that goes through the double bond. And on each carbon, we're going to decide which one is our high priority group. So I'm just going to erase the locants so we can not get too distracted while we decide what is high priority here. On this side, so this carbon here, we have a fluorine atom versus a carbon atom. And fluorine has a higher atomic number than carbon. So this side is the priority, it gets the P. On the other carbon, we have a carbon and a carbon. So we have to go 1 bond away and compare. So this carbon, the methyl, is bonded to H, H, and H because it's a methyl group, CH3. This carbon, of course, is bonded to another carbon and then 2 hydrogens. Remember, they're the implicit hydrogens. They're omitted. So it's got a C and then an H and an H. So it's got a C. The other one just has 3 H's. So this side is the priority. So now we have both of those P's on the same side of that plane. So same side is Z. So we put our Z in parentheses in front of the entire name. The next example is asking us again to draw. We'll start with the parent. Let's highlight that in pink because we always have our parent in pink so far in this course. And then our substituent is going to be a 1-methoxy. Let's look at the pent-1-ene part. So pent means 5, so we know we're going to have a 5-carbon chain. We also know that we're going to have a double bond on the first carbon of that 5-carbon chain because we have a pent-1-ene. 1, 2, 3, 4, 5. I'll just do my dots here so you can see that's the 5-carbon chain. And then we're going to put a double bond on the first carbon. Okay, so there's our pent-1-ene, and we're going to be placing our methoxy group on carbon 1. So a methoxy group looks like this. So O and a CH3. So we've got to put that on carbon 1 here. We have to do that so that there is E stereochemistry. So it's important to remember what that means. So E means that if we look at this plane going through our double bond, that the priority groups are on opposite sides. They're enemies for E, right? So on this carbon, carbon 2, I'll just label carbon 2, we have the rest of the main parent chain, and we also have a hydrogen substituent. Remember, we leave those off in the skeletal structure, but you'll understand this better if I draw it in. So our priority group between carbon and hydrogen is the carbon side. So our priority side rather is this side. So I'm just going to label that P for priority. And so we need to place the methoxy group so that the priority group is on the opposite side of that plane so that they're enemies. And of course, the other thing that's going to be on carbon 1 is a hydrogen. And so in order to make it E, we're going to place our methoxy group over here. O, and then that methyl. So this whole substituent is the priority. And then I'm just going to erase that number 1 so I can draw in the hydrogen. So that would be E1-methoxypent-1-ene. Here is a ring. We haven't done any rings yet in this section, so I'm going to talk about rings a little bit, but first we can just count the carbons. This is a 1, 2, 3, 4, 5, 6 membered ring, so this is a cyclohexene. Okay, and we are going to look for substituents, and we have a nitro group here. Nitro, so we're going to have nitro cyclohexene. And finally, we're going to number this structure and give locants. And so remember, in rings, since there aren't ends, we get to decide which carbon has the number 1. We're going to prioritize the double bond. So if we number it here as number 1, then we'd have 2, 3, and 4 for the nitro. If we did the other end of the double bond as number 1, this is just to show you what would happen. If we gave this the number 1, we'd have to number the other side of the double bond as number 2, and then we'd have to go around the ring this way to get to the nitro, so that would give it 5. So the black numbering that I did is better. So hopefully you believe me that we've got a 1 for our double bond and then a 4 for our nitro substituent. So 4 nitro, cyclo hex 1 ene. And this is just a little note for future reference. You probably won't run into this very often or ever in a regular organic chemistry course, especially one that doesn't focus much on nomenclature. But when you have rings with double bonds, if the ring has less than 8 carbons, you don't have to specify the stereochemistry. And that's because the ring is too small to ever have a trans double bond. And so they're always going to be cis, and we can just leave it out. So less than 8 carbons, no stereochemistry. More than 8 carbons in a ring, you do have to specify E or Z or cis or trans. Now the last example is another one where we're going to draw. So it's asking us to draw 4-bromo-oct-1-ene. So we'll start with our parent structure. So that's going to be an octene. So 8 carbons with a double bond coming from the first carbon. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to draw a double bond on that first carbon. So there's my oct-1-ene. And then it is telling us to add a bromo substituent on carbon 4. So I'm just going to go 1, 2, 3, 4. We'll put a bromo there. And that is our whole structure for bromo-oct-1-ene. And the reason I chose this example is because I wanted to show you another example of an alkene where you don't have to specify the stereochemistry, and that's because we have it on the terminal position, on position 1 here, and there's nothing else bonded to the other side of this alkene except the hydrogens that are implicit in that skeletal structure. So we don't show them, but they're there. Because there's 2 hydrogens on this end carbon, there's no stereochemistry, because if we swapped these 2, we'd get the same compound. And so there aren't 2 stereoisomers of this molecule. Now, if you ever come across a molecule that has more than 1 double bond, here is how you name it. And these structures are called polyenes. So what you would do is you would try to include all of the double bonds in the parent structure. So in this example, we have a cyclic parent, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 carbons and 3 double bonds, and they're all included in that parent structure because they're all within that 11 carbon chain. So what we're going to do for the name is we're going to take the number of carbons plus A, that's for pronunciation's sake again, plus the multiplier, so tri in this case because there are 3 double bonds, and then ene. And so the parent name of this large structure is cycloundecatriene. I just highlighted that so you could see. Cyclo because it's a ring, undec is the root for 11 carbons, and then A for pronunciation, tri for 3 double bonds, and then ene for the alkene. So that's quite a mouthful. And then if you notice, we have E and Z locants in parentheses at the very beginning of the name here. So 1E, 4E, 8E. So the E and Z stereochemical designations for those 3 double bonds are way at the beginning of the name. They're in parentheses, separated by commas, and each one includes the locant that it refers to. So here's a little challenge. Look at the rest of this molecule where all the substituents are and the double bond stereochemistries and see if you can figure out the numbering and where carbon number 1 is on this molecule. So you may run into a situation where you need to name a double bond as a substituent instead of in the main parent chain. So you're going to name it as an alkynyl substituent. To get that substituent name, you'd take the number of carbons in the substituent plus enyl. So En for the fact that there's a double bond and il for the fact that it's a substituent. So you've got enyl. And we also have to still specify E and Z within that substituent name. So I'll show you an example here. So in this example below, we're just going to look at the substituent. So that's this little chain that's on the bigger parent ring. And it has 3 carbons. And it's got a double bond between the first and second carbon of that 3 carbon substituent. So this is going to be called a prop 1 enol substituent. And we also have to include that E and Z notation if there's possible stereochemistry for that double bond. And so if we look in, we have the full name underneath this. So this is a Z prop 1 enol substituent. And that's because this is the priority and this is the priority, and they're on the same side of this plane. And so it's a Z prop 1 enol substituent on the rest of the molecule. All right, in the last part of this section, we're going to talk about what you do if you have a double and a triple bond in the same molecule. And so molecules with double and triple bonds in them are called enynes. Very creative. So we're going to try and include all of the double and triple bonds in the longest chain. We're going to name it for the number of carbons and then enyne. Enyne refers to when you have one of each. If you had 2 double bonds and 1 triple bond, it would be dienyne. If you had 1 double bond and 2 triple bonds, it would be endiene, and so on. So then you're going to find the lowest set of locants for all of the double and triple bonds. And if you have a choice for the lowest set, you'll give the double bond the priority for having the lower number. So I'll show you what I mean by that in one of my examples. But let's go through an example here so you can see what I mean, how to name an enyne. So we've got 1, 2, 3, 4, 5, 6, 7 carbons on this little molecule here. Remember this alkynes terminal, so it's got an implicit hydrogen there that isn't drawn in, but it's understood to be there. So that's hept enyne. All right, and we've got to do our locants here. So if I number this way, I get 1, 2, 3, 4, 5, 6, 7. And if I number the other way, I get 1, 2, 3, 4, 5, 6, 7. So with the black numbering, I have a 3 and a 6. And with the pink numbering, I have a 1 and a 4. So the 1 and the 4 is better. So it doesn't matter that the alkyne gets the 1 and the alkene gets the 4. We just care about the lower set of numbers. So I will erase the black ones so as not to confuse us. All right. So putting this all together with the locants included, we're going to get hept 4 ene 1 ine. Now I'm going to do one more example just to clarify what I mean that when there's a choice for the lowest set, we prefer the lower number for the double bond. So here's another ene. We've got 1, 2, 3, 4, 5 carbons. So this would be a pent ene. Okay, we'll number this way. We get 1, 2, 3, 4, 5. So we have a 1 and a 4 for where our double and or triple bonds start. And if I do the other direction, we got 1, 2, 3, 4, 5. So we also have 1 and 4. The only difference is that you got a triple bond on 1 and a double bond on 4, or vice versa. And so how do we choose between these sets? We have a choice for the lowest set here. And so we're going to choose the set that gives the double bond the lower number. So that's the black set here. So the double bond gets to be 1 and the triple bond can be 4. So that's what I mean when there's a choice. So this would be pent 1, oops, forgot my dash, 1 ene 4 ine. And that's how you do it for an E9.